Hi everyone, so now we're on to C4 parametric equations. And what is a parametric equation? Well, Cartesian equations, which you may or may not know, from our functions work we know that Descartes created, the philosopher, moved from mapping functions, didn't he, onto away from bubbles. So mapping onto graphs. So two variables, in other words, x and y, t and x, z and g, whatever. Two variables means it's in Cartesian form. Parametric form, however, is when you add a new parameter. So x and y are parameters, but if I add another one, z, in there, then that's another parameter. So if you've got z in terms of x and y, then in theory that's parametric form. Or if you add another variable t in there, do you see what I mean? So parameters, when parametric form is when you're adding another parameter basically, and you are, well, you'll see, splitting up your function into two kind of separate equations using that new parameter. Why would we want to do that? Well, let's take this case in point here. So x squared plus y squared is 1. We know that that's a circle and it's centered at 0, 0, and it's the unit circle, which means it has radius 1. If I ask you to find and locate 3 unique points on this circle, it's not actually as easy as it sounds, is it? Because you would have to first rearrange that equation, I guess, and you'd have to plus or minus square root it, yeah? And then you would put in values for x. So let's say if I wanted to put x equals 5, I get 1 minus plus or minus, because I want to find my y value, yeah? 1 minus 25, now I'm taking the square root of minus 24, which of course I can't do, and my nose will start bleeding. What values can I pick? Well, if you know something about the circle, then of course you know that this is going to fluctuate between 1 and minus 1. But that's because you know that, and therefore you know that if you pick values for x, I don't know, 0.5 squared, let's say that will work, or 0.3 squared, you'll be able to find your 3 coordinates. But that's only because you know that x squared plus y squared is 1 is a circle. If you didn't know that, you could be wandering around for a while trying to find values that could work. There is another way of describing a circle though, and this is where the parametric form comes in. So let's say we drew that circle to illustrate this point. Here's a point on the circle which we know has coordinates x, y. Do you see? If we build um, a radius going along that, so from the origin to P, we can split this x and y up, can't we? So here's x and here's y. And here, let's say, is a value of theta, an angle. So I could describe, if this was length 1, so that radius is length 1 in this case, isn't it? I could describe x in another way, couldn't I? Because I know that cos theta through SOHCAHTOA is x, the adjacent, over the hypotenuse 1. Yeah? And therefore x is cos theta. Y, if we go sine y equals opposite, that's y over hypotenuse, that's 1. And therefore y must be sine theta. Do you see? This is now in parametric form. We've added a new parameter. We've added this theta in here. There's a third variable. And now it's really easy for me to find points. I could let theta be anything. I could let theta be, because it's just rotation, isn't it? And it can infinitely rotate round. I don't even have to think about it. I could put theta equals 5, 6, 10, 9, minus a million, whatever. I'll always get a value of x and y, won't I? so I can find every point on this circle. Let's try that again. This time I've got x equals 4 cos t and y equals 3 sin t. I don't really know what that is, what I do, but you know, how how does this is in parametric form because I've got an extra parameter t, so I've got three variables. What's this thing going to look like? Well, I could, whack in loads of values of t, start plotting out my points, right? Or I could, do you see what I mean? I can put any value of t in there and everything will be absolutely fine. I'll always be able to plot my points. Um, so I could try t equals 0, I could try t equals pi, pi by 2, pi by 4, pi by 6, etc. Okay? How would I put this in Cartesian form? Because maybe in Cartesian form I'll be able to see, maybe it's a known function and I don't need to waste my time looking for it. Well, if x equals 4 cos t and y equals 3 sin t, we knew from that circle before that if I made it general, let's say the radius was r this time, not 1, therefore x is going to be r cos theta, isn't it? And y is going to be r sine theta. Just going back here, taking instead of that 1, we make that r, and therefore the r comes up. Yeah. And how can I know that that's correct, that x and y? How do I know that makes the circle x squared plus y squared equals r squared? Well, think about it. If I say x squared plus y squared, then x is r cos theta, so that's r squared cos squared theta, plus and y squared is r squared sine squared theta. Take out the factor of r squared, and cos squared plus sine squared we know is 1. So there we go. We've built a Cartesian form. We're going to do exactly the same thing here, except can you see this time I need to get, if I see a cos and a sine, I know I need to get the cos and sine by itself. So if I get x over 4 by itself equals cos t and y by 3 equals sine t, then you can apply the same logic again. So x over 4 squared plus y over 3 squared is going to equal cos squared t plus sine squared t, which is 1. So this is x squared over 16 plus y squared over 9 is 1. And this, you may or may not know, is an ellipse. And an ellipse looks like this. This is in FP3, so you don't need to know the equation of the ellipse, but this is interesting, and it also illustrates why parametric form is so good. Because what kind of things work with ellipses? Why would we model ellipses? Well, satellites, for instance, space, because they orbit, don't they? They go in an oval type fashion. So ellipses are really good in parametric form for a number of reasons. Because look, if I take any point on this ellipse, pxy, if I use this equation, all this tells me is the shape of this curve. That's it. Whereas this one can tell me so much more, because what happens if t was time? What happens if t was, say, 4 months? And then I whack in t equals 4 into x and t equals 4 into y. I'd end up with a point here, right? If I whack in t is 10, so after 10 months, maybe I'm here. Do you see what I mean? It gives me a whole new set of information that I can predict when 5 months down the line, my satellite is going to be here. Also, parametric equations are really helpful to describe circular functions. So an ellipse and a circle, a spiral, these are all circular functions. Um, and therefore they can describe nature so much better than Cartesian form, because Cartesian form works on a kind of square system, doesn't it? Have you heard of that phrase that nature or God doesn't work? The phrase is God doesn't work in straight lines, or nature. There are no straight lines in nature. Yeah, and therefore, what you might have heard of them called polar equations, and parametric equations are much more realistic in modeling the real world, much more smooth, circular, easier equations to work with. And we'll talk a bit more about that with a challenge question in class. So we've done the what would the Cartesian form look like, but like I said, it's if you've got an equation in parametric form, it's in that form for a reason. It's the most elegant or neat way to describe a circular function. So don't change functions into Cartesian form because it can be really nasty. And in class, I'm going to give you a challenge question where you see how horrible it is sometimes when the parametric form is so simple. So you don't change into Cartesian form unless a question asks you to. Because what's the point? You just make your life so much harder putting it into Cartesian form. So this is something Edexcel want us to do, and we'll jump through their hoops, but there's no point doing it otherwise. Now this other bit says, how do you find the tangent to the equation? Well, this is where we need to use the chain rule. Because if we had x equals 4 cos t, y equals 3 sine t, I could do this one, obviously implicit differentiation. You know how to implicitly differentiate. But again, what's the point? Let's go for the parametric form. And we know from the chain rule that dy by dx is dy by dt, dt by dx. And that's exactly what we're going to exploit now. So to find a tangent, first off, we need a gradient, don't we? So we need to find dy by dx. So dy by dx equals, well, dy by dt, the differential of this, is 3 cos t, isn't it? Now dt by dx is the same as 1 over dx by dt, isn't it? And dx by dt is minus 4 sine t. So I recommend you just instantly go 3 cos t over the differential of your x, so minus 4 sine t. I hope that makes sense. So this is your gradient function now. And remember, to find a tangent, we need a point, don't we? Now this bit you might find a bit hard, potentially, if you're not really sure what's going on. I haven't given you a specific point yet, because we know we need to go into y minus y1 equals the gradient, which we've just said is that, times x minus x1. In order to get an x1 or y1 value, I need to have a value of t, don't I? To get a specific value. But I don't have a point because I want to know the general equation of the tangent anywhere. So if p is here, or if p is here, that's a tangent, or if p is here, that's the tangent. Do you see? So I'm giving a general tangent equation. And the point P anywhere is xy, isn't it? But we've just said x is 4 cos t and y is 3 sine t. So unless I've been given a specific value of t or an x or y value as a point, I can just put in the general version of my tangent, you see, of my point, where p is x, y, but x and y are described in terms of t. Let's try another one. So I've got a curve here, x equals, oops, x equals 1 over t plus 1, and y equals 1 over t take 2. what does that look like? Well, it looks like this. This kind of weird, I like to think of it as kind of a Spider-Man web or something, you know, go web go. Um, this weird kind of skewed H. Really cool graph. Wouldn't want to describe that in Cartesian form necessarily, uh, at the moment anyway, because it doesn't look very nice. So we're not going to. We're going to find the normal at the curve at t equals 1, because I haven't been told yet to convert it. So, same again, dy by dx equals, well, first we're going to have to get this in a form we can differentiate. So this is t plus 1 to the minus 1, isn't it? And y is t minus 2 to the minus 1. So dy by dx through the chain rule is dy by, whoops, dy by dt, dt by dx. And therefore dy by dt, differentiate that, the chain rule, minus comes down, t take 2 to the minus 2, differential of the inside goes to 1, times by dt by dx. Remember, we're just going to put that as over. And now chain rule of this one. So minus comes down, t plus 1 to the minus 2, and t inside goes to 1. So there we go. You could clean this up a bit if you want. So this is minus 1 over t take 2 squared, all over minus 1 over t plus 1 squared. Minuses cancel, bottom flips up, so t plus 1 squared over t take 2 squared. And we're looking for the normal at the point t equals 1. So at t equals 1, dy by dx is going to equal, when t is 1 in there, that's 1 plus 1 over 2, so that's 4 squared, because it's 2 squared, and 1 minus 2 is minus 1, all squared is 1, so the gradient is 4. Sorted. So straight into y minus y1, gradient x minus x1, except hopefully you're screaming out, no, it's not that gradient, because we're looking for the normal. So actually, m2 is minus 1 over m1, isn't it? So actually this should be minus a quarter. Okay? And hopefully you're screaming out, we need a point then. So at a point P, how do we find the point P? We need to know the x and y value. And how do we get that? Well, t is 1. So t is 1 needs to go in there. So x equals 1 over 1 plus 1. So that's a half. And y equals 1 over 1 minus 2. So that's minus 1. So now this is y minus 1, so that's plus 1. And then x minus a half. And then we found the normal equation. Next video then.